Okay, continuing with platings and coatings and the passivation and pre-oxidation, and right now perspiration, so we'll get rid of the coat and proceed. Now, stainless steel fasteners are normally passivated or pre-oxidized during the manufacturing process to make them more inert. And of course, I mentioned earlier it's done with a acid treatment, and then of course the pre-oxidation is just done simply by putting them in a furnace and run them up to about 1300 degrees and cooling them to form an oxide coating on the surface. The advantages are that it deters galling, and it's a relatively inexpensive process. The disadvantage is that mating parts still need to be lubricated for torque coefficient consistency. And here's the old familiar black oxide coating with oil. And it's nice and pretty and black, and you put oil on it and it glistens and looks good. But once the oil is gone, black oxide is worthless. It's real cheap, no baking required after plating it. The material strength is less than 200 KSI. And its disadvantage is it's worthless for corrosion prevention once the oil is gone, and the coating doesn't adhere well to steel. Now here's a bunch of miscellaneous platings and coatings, and electricless nickel is one of them, and it is used a lot on just coating of steel where you don't have threads, but on threads, it creates some problems in that you can get uneven plating on the threads so that they're kind of out of tolerance. This Sermatel Sermalloy is a aluminum inorganic material that is used for corrosion protection of both unthreaded and threaded parts. But once again, if you assemble, reassemble very many times, it will come off. Synergistic is another one. It's a combination of surface oxidation and a fluoropolymer used for corrosion protection and lubricity. But these, for assembly, reassembly, none of these work that well. On proposed replacements for cadmium, of course, there's been a big push to do away with cadmium because it is such a bad thing environmentally. So there's an outfit over in Chardon that came up with this Dacromet 320 with a plus L sealer as a proprietary thing for the automotive companies. And it has metal oxides, zinc and aluminum, and a clear sealer. It's good up to 600 degrees, but the coating is damaged by disassembly cycles, and it will support fungus growth. And it costs about the same as cadmium, so the cost savings isn't there. The only thing that it's kinder to the environment. The zinc nickel coating is one that is used some. There's about 90% zinc and 10% nickel, but it doesn't work very well on fasteners. It works on rods and things of this nature. Now here's a summary of platings and coatings. And the thing that is most important here is the useful design temperature limit. You will notice that most of these don't go that high. And the A here is for the black oxide with oil. As soon as the oil boils off, your corrosion resistance is gone. So you see, when you get down to it, about 1200 degrees is the best that any of these will do. So that's why that in a lot of cases where you have super high temperatures, you have to use a material that doesn't require coating, like wasp alloy or a Haynes or Inconel or something of that nature, because you can't rely on the coatings. Now here's a table that just gives various characteristics of the coatings and plated. There's a couple here that I wanted to mention. Iridite is a common coating In fact, we used it on the CM1 chamber, for it is electrically conductive, whereas anodized isn't. And it is a type of chromate conversion coating in which you actually treat the surface with an acid to form a real thin layer that is somewhat corrosion resistant. So what we had to do on CM1, you mask it in the irradiated areas where you have electrical conductivity required, and then the anodize, which is actually used, although it's used on other materials, we know it as being used on aluminum. It is a acid etch using sulfuric acid, I believe, that forms a fairly heavy oxide coating. And in fact, you can't anodize a fastener because the anodize is thickened. Well, you can anodize it physically, but it doesn't work out very well on the threaded areas because you'll have too heavy a coating in the threads to where it doesn't work too well. Now, moving on to thread lubricants. There's all kinds of lubricants available, and of course, all of us have used the old 10W30 oil and for our cars to lubricate stuff. The oil, grease, wax, graphite, silver, molybdenum disulfide, and proprietary types such as Never-Seas, Silver, Goop, Synergistic, and Everlube, and so on. Some of these are applied at installation, and some are cured on the fastener by the manufacturer. I'm having trouble turning my page. Okay. For oil and grease, you have good lubrication up to the boiling point of the oil or grease, which is usually around 250 degrees. And of course, you can't use any of this stuff in vacuum. Now, graphite. Dry graphite is not dry. It's a fine carbon powder that needs moisture, usually oil or water, to become a lubricant. And then when the moisture evaporates, it becomes an abrasive powder. And of course, it can't be used in a vacuum either. Silver plating, as I mentioned earlier, it is normally used on stainless nuts with stainless bolts as both a lubricant and anti-galling coating. And it's good up to about 1600 degrees. It can be used in a vacuum, but it is very expensive. Molybdenum disulfide is kind of a universal type that's used in the aerospace industry because it's can be put on as a dry film lubricant. It's good up to 750 degrees. It can be used in a vacuum, and it can be applied to both alloy steel and stainless steel. Now, Never-Seas is a proprietary petroleum-based lubricant, and it contains metal oxides, usually copper or nickel, depending on what temperature you want, because the copper, of course, has a lower melting point than the nickel. And it's good up to 2200 degrees, because what you wind up with is the metal flakes between the threads as the oil boils off. And so this means that you have to reapply each time you reassemble it, and it can't be used in a vacuum either, but at least you have the flakes in between the threads, making them easier to disassemble. Silver Goop, which is made by some company here in Cleveland, I believe, is a proprietary paste that contains 20 to 30% silver, and it's good up to about 1500 degrees. But of course, silver is corrosive to aluminum, magnesium, so you don't use it on them. It's of course, the Silver Goop is very expensive, and it can't be used in a vacuum either. The fluorocarbon coatings, there's a lot of them available. I'm just listing a few of them here: the Synergistic, Stancoat, Stalgard, and Everlube. And they're only good for a few assemblies because they flake off if you assemble and disassemble a fastener nut and bolt very much. And they're only good up to about 400 degrees. They can be used in a vacuum. And here was one that I learned when I was looking for different types of lubricants for high temperature applications. Plain old milk of magnesia is used by the turbine engine companies for engine assembly, because anything that you use in a jet engine for a lubricant is going to burn off anyway after the thing's operating, but in putting it together, this is a suitable lubricant, and it doesn't harm anything when it burns up. Now here's a summary of the thread lubricants, and most of the stuff we have covered here, doesn't necessarily include all of them, but these are the common ones. And once again, there's very few that are good for high temperatures. Here are the 3 that are good for the high temperatures. So this is something you have to keep in mind, that going back to that original principle, that the first thing you want to do is establish the environment that you're going to have your fasteners in. Now, going into the subject of corrosion, of course this is a major field, so we'll just try to hit it a little here in the way of fastener corrosion. Galvanic and stress corrosion we've already covered, and the corrosion resistance of a particular metal to a corrodent can be found in a book of tables, which I will be leaving behind when I retire. It's a 2-volume set that actually gives, for the different percentages of different types of corrodants, it gives the effect on the various materials. And hydrogen embrittlement and graphite corrosion will be covered in the corrosion section here. Hydrogen embrittlement, it's talked about a lot in recent years, and yet you can test for it, but it's kind of like a UFO, it's kind of hard to find. It's caused by having free hydrogen ions in the presence of the metal, which in most of the time it's steel that it causes problems in, during the manufacturing or plating process. The higher the strength of the material, the more sensitive it is to hydrogen embrittlement. Now, you can get a hydrogen chemical reaction in which it combines with the carbon in the steel to form methane gas or hydrides with the titanium, niobium, columbium, same thing. The English call it niobium, the Americans call it columbium, or tantalum to form hydrides. The methane gas can cause cracks, and the hydrides are weaker than the parent material, so they can weaken the material. Then you can get hydrogen blistering, where the atomic hydrogen fuses into the material and combines into molecules, and then the molecule is bigger, so it can't get back out. So it'll build up pressure to create blisters that will eventually cause cracks. And here's the problem. There's no external indication that hydrogen is present. You can't look at it, you can't run it through an X-ray machine, anything like that, and find out that it's there. So the only thing that you can do is test for it. And the way they test fasteners for hydrogen embrittlement, they put them on a fixture. There's an ASTM spec, which I'm not, I don't remember the number of it. You actually put them on with a wedge type washer and tighten them down and leave them for, I think it's 48 hours or something like that. If the head didn't pop off, it passed the test. And that's so what they do on testing for hydrogen embrittlement is just take a bunch of samples and test them that way to see if they can find where any of them have embrittlement. Now, on hydrogen environment embrittlement, usually you wouldn't run into that because it takes high pressure hydrogen to cause that. So if you had a tank of some kind, a high pressure tank that you had fasteners holding something together inside, then you could actually get hydrogen into the fasteners just from the high pressure. In other words, we're assuming there was no hydrogen embrittlement in the fastener before it was installed. Then you need about 2,000 psi hydrogen in order for it to go in the material after it's installed. So that's not likely to happen, but hydrogen embrittlement is always a problem because it depends on how good the manufacturer was at making the part. So here are some precautions. Use the killed steels, coat and plate the fasteners, bake the hydrogen out within 2 hours after plating, otherwise you can't bake it out. Tailor the plating bath to minimize free hydrogen ions and avoid the use of alloy steel fasteners above 190 KSI because the only way you can plate without getting hydrogen embrittlement is to do it in a vacuum atmosphere. Then use stainless steels that are not sensitive to hydrogen embrittlement and run the tests to see if you can find any evidence of any embrittlement. Here's one that is slightly different in your book that had a revised it at the last minute. The definition of the graphite here, just to indicate what it is, actually it's a dry film carbon lubricant which can cause corrosion when exposed to moisture because on some materials it can cause you problems, and I realize that they put out a lock ease, or they used to put it out, which is a graphite in oil to use for locks. But yet it will corrode some types of locks, so a guy by the name of Gilbert gave a course on corrosion here several years back, and he pointed that out, that graphite was a no-no for lubrication of locks for that reason, because it'll actually corrode a lock. And one of the things, and this happened to us on one of the turbine engine programs around here, is dry graphite is an abrasive. So if you cook it and dry it out, now you have a carbon powder abrasive, which does a lot more harm than good. And here's something I threw in just for your information. I had run into this in a failure course that I took. Dezinctification, it's kind of an odd word, but you can actually get in a material that has, it's even used for just removal of a particular element from a material by corrosion. But usually it's the removal of zinc from brass by chemical action leaves a brittle shell of copper. And I saw one of the samples the guy had, and you could compare it to what happens to a wet piece of wood once the carpenter ants get done with it. It's just a shell that you can crush. And it's rather striking to look at a failed piece like that. So here's the galvanic series, which I had been talking about earlier. In fact, I believe we showed it earlier, that shows the different materials. Now, of course, magnesium is right at the top. And magnesium is a disaster in a corrosive environment. In fact, this guy who taught a course on failure analysis pointed out that when an airplane goes down in the ocean, one of the ways that they look for it is if it had zinc components in it. The zinc will decompose so fast in the salt water that you'll have bubbles coming up out of the ocean, and they can look for it. So magnesium, I'm a member of the Mill Handbook 5 committee. I don't know whether some of you are familiar with it or not, but anyway, it is kind of the Bible of the aerospace materials world. And magnesium is kind of out of usage by the aircraft manufacturers for this reason, because it is so hard to protect it from corrosion. And it's not used in any primary structure that I know of on any of the airplanes. Okay, going on to locking methods. In most any application, some type of locking must be used to prevent the fastener from loosening under load. And without a locking device, of course, the only resistance you have is just head friction and nut friction, which, if you are vibrating it very much at all, is not enough. Now, fine threads give you slightly better resistance to loosening from vibration than coarse threads, but it's not a lot due to the flatter angle of the threads. And one of the things that you try to do, and this will help you once in a while, is to mount bolts with the heads up to lessen the loss of loose bolts, because sometimes maybe you'll find something on your car that the nut's gone, but the bolt's still hanging there, flopping back and forth, and you can go ahead and put a lock nut on it. Now, here's one of the most common type of locking methods is deformed thread. And what you do with the nut, it's usually on the nut, after you have formed it, the last operation, you actually hit it from two sides and make it slightly oval. Then when you put it on, and this hit's got to be controlled too, because otherwise you can be in a heap of trouble, it will kind of go back to circular again. So that's, see, initially here it is oval. Then when you put the thing on, it goes to circular. It will actually deform enough. And of course, when it does that, the threads will lock up on the bolt. Then when you take it off, it will go back to oval again. So you can use this one around 10 times before it loses its locking capability, because eventually, putting it on and off, you're going to yield it back to the circular condition, and it will no longer lock. But that's one of the good ones, and you can buy deformed thread lock nuts at your hardware store. Now, here is the locking collar type, and although I didn't call it out, your elastic stop nut is one of the biggest manufacturers of these. What you have is you have a fiber or a nylon collar here in the top of it. The collar has a smaller diameter than the bolt thread, so when you run the bolt in, it will interfere on that collar. And it'll also provide a little bit of sealing. If it'll kind of seal from getting water in there. It'll give you that much sealing, although it's not for pressure or anything like that. But the only problem is this collar is usually only good for about 250 degrees to where it will start softening up to become ineffective. Now here's the split beam lock nut. This is one that works quite well. And what you have a smaller diameter at the top of it, and it's saw cut, so that when you put it on, it'll spin freely till it gets up to that area. Then as you tighten it up, the beams, if you will, these 6 beams on it, have to deflect outward in order for the bolt to go through. So once again, this gives you a pretty heavy friction load on the threads and will lock it in place. I had a personal experience with one of these on a car that I had that the shock absorbers didn't want to stay on it, and I put these split beam lock nuts on it, and that held, versus the jam nut, which I'll cover later. Now here's the Nylock pellet. Now Nylock is the biggest manufacturer of this type of thing, although it's even covered by a mill spec, so there's a lot of people in on the act on making it this way. But what you do is you cut a little hole in the thread and stick a Nylock plug in it, and this plug sticks out past the thread, so when you put it on, the nylon will bind up in the threads and cause it to lock. This one is a fairly good cheap way of locking stuff. You can use it on a bicycle or a lawnmower or something like that. It'll hold up. But once again, the temperature range on it is kind of low because nylon starts getting soft at about 250 degrees. And of course, the threads will chew it up, so you can't put the thing on, take it off very many times without running into trouble. Now here's Loctite, which we use around here all the time. That's actually a trade name, but different people make this. It's actually a one component type adhesive that you just smear on the fastener before you assemble it. And it's made in different grades so that if you want to remove the fastener, you use the less sticky type. Like in Loctite, I think 242 is for removable, and 271 is the tamper-proof fasteners, and there's another one or two in between there for bolts that you just want to make difficult to get off. But some of the manufacturers, other manufacturers of this are Bostik, ND Industries, Nylock, 3M, Felpro, and Permabond. And Loctite is good up to about 400 degrees. Now, epoxy ribbon, this is used a lot on bolts. You get them and they have two ribbons of epoxy so that you have the main one and then you have the hardener that goes with it. And this way you can store them. It has a shelf life, at least, that you can keep them for, I think, up to a year or something like that. And the epoxy is mixed when you install it, so it will combine and harden to hold the fastener in place. Now, of course, this type, once you would remove it, it would have to be replaced because you destroy the seal because it's a one-time type thing. And the maximum operating temperature on these is also about 400 degrees. Here is another type of thread that's a special thread, Spiralock. I think Detroit Tap and Die is the holder of the patent on this one. And this is a cross-section here of a tapped thread and a fastener. Now, the problem with this when you install it is you have to have Spiralock's tap because this is an oddball. See, the thread, the tapped hole does not fit the thread, and you get your locking action by actually wedging the ramp of the thread up against the oddball type tap. And but you can distribute over several threads, so it offers better locking capability than ordinary thread would. And some people have used it and run vibration tests, and it holds up fairly well. But of course, the disadvantage is that you can't. You have to get their tap to tap the hole initially, and so that creates a problem sometimes for people on universal type assemblies. On the direct interfering thread, in this case, you just have a fastener that is made deliberately with an oversized root diameter to give a slight interference fit to lock. Now, some studs that you have where you have a stud that is installed in something and you want to leave it in place, you use this type of thread so that it will not come out when you take the nut off the other end. The tapered thread is kind of a variation of this in which you actually taper it. This is a smaller diameter up in here. And then when you put it together, it has to push the threads out here, and that gives you a locking force on it. Now here's one that we covered in the drafting room manual stuff that Ron Romanchuk, we fought semantics on that one a lot, whether it's a castle nut or a castellated nut. So since I wrote this, I put my preference in as castellated nut with a cotter pin. This is used a lot for installing bearings and things like that where you don't want to tighten it very tight, but you want it to stay put once you tighten it. So you can tighten the nut up, then to the torque you want, then back it off or tighten it to the next spot on it to get you a slot, because you only have a single hole drilled in the end of the fastener. So you line up one of these slots with that hole. Then put a cotter pin in it, and it will hold it in place at the exact spot that you set it. This way, when you're, for instance, a lot of the cars are made this way. There's another way that will be my next slide, I think. But on wheel bearing, when you tighten it up, usually you tighten it up tight to seat the bearings, then back it off enough to let it spin so the nut is a little more than finger tight. Now here's another one that is used for the same reason. Evidently, this is cheaper because you're doing the same thing with a regular nut. Then you're taking this nut cap, which is a sheet metal, stamped sheet metal piece, but it has the serrations here with the slots in it that you can put the cotter pin in. So you torque the nut to the spot you want it, then slip this thing over it, then put the cotter pin through the hole in the axle or shaft, whatever it is, and fasten it the same way as we did on the other one. And of course, the reason that grease cap is on there is I got this diagram from a truck manual, and I didn't separate the grease cap from it. That goes on after you've installed everything else. Now here is lock wiring, which is normally used just by the aerospace industry because of the cost and labor involved, because you are winding these wires on here through either holes straight through the top of the heads, or in the case of the nut, holes through the corners of the nuts. You put these on in such a pattern that if you try to loosen one fastener, it tightens the other one. This way, they can't loosen because they're all tied together. And this is a method that is covered by an MS spec 33540. You can use it quite well where you have a circular pattern of fasteners on a flange or something like that. But the only people that use it in normal cases is the aerospace industry. Here is an alternative method to the lock wiring. This is a similar thing in which you start out with a piece of cable by the Bergen Cable Company here that has a ferrule already swaged in place on it. So you just feed it through. You run the wire through the heads to wind them the same way so that one can't loosen without tightening the other one. Then when you get to the end, you have a machine similar to a rivet gun or something that actually puts a ferrule on here, pulls the right tension on the wire, and closes it off, so that this is actually a faster and cheaper way of lock wiring than the standard lock wiring method with the twisted wire. This is the disc lock washer. It is a little bit cumbersome in that you have a pair of washers together, and these lines here represent the angles on them where you put the two together and turn them together. Now, as long as you keep them together, they can't rotate with respect to each other. So the angle of this ramp is steeper than the angle of the thread, so it will keep it from turning. However, the bottom and top of those two washers have to have serrations on them that bite into the joint material, and also the bottom of the nut, in order to keep it from slipping with respect to the nut or the joint. Otherwise, the washer will spin as a unit and doesn't help you any. So that one will work if you are not concerned with tearing the coating loose on the surfaces. Here is a kind of a takeoff on the disc lock washers, in that you have a nut assembly. Now this one has the ramp here, and the lower part of it from here down is not threaded, just the upper part's threaded. Well, you see, you put the two of them together, you put them on with a socket that extends down over both of them. Now, this will hold the thing while you torque it up, and then, of course, the bottom surface of it has the serrations on it that bite into the attaching plane of the joint. So, once again, you're scratching the surface you're attaching to. However, a company out on the West Coast makes these, and the president of it told me that they were selling millions of these for the heavy truck industry, because the heavy truck industry's had a lot of trouble through the years with nuts coming off and wheels coming off. So, so they're paying for this type of nut in order to hold them on, because they do work on holding truck wheels on. Here is another method. This is a Duralock nut, which is a trademark of SPS, which is one of the big manufacturers of fasteners. It has serrations on it here that bite into the surface so that it will not slip and start loosening up once you get it tight. Now, you have to depend on this embedment of the serrations in the contact surfaces, and so it will scratch up the surface. If you can live with that, this one will do a pretty good job of locking. Here are tooth lock washers, which are common in the electrical and automotive industry, because they do afford locking, but once again, they do it by gouging into things. These teeth are twisted. Although this doesn't show it, they're actually twisted so that you have one surface bites into the fastener, the other one bites into the surface that it's up against, so that it will get enough bite on both of them to hold them in place and prevent rotation. However, you damage the surface quite a bit. Now, this one is also available with teeth on the inside, so that the outside is smooth in areas where you don't have room enough to have it stick out that much. You can get them with the teeth on the inside. Here is the old famous jam nut, which is one that if I polled the people in the audience, neither one would be able to give me a positive answer on which side you put this one, whether you put it here where it's showing, or you put the big one on the inside and the little one on the outside, because the experts can agree on that. It's difficult to load each one of these so that it'll carry any load compared to the other ones, because if you tighten this one tight, it will unload this one, and if you don't tighten it enough, then the two of them will not work together. So it's very difficult to get both of these loaded to where they would carry a load. So jam nuts, in my opinion, are not to be used for critical designs unless it's something like locking a turnbuckle or some sort of a rod where something else carries all the load and you're just pushing this up against it to keep it from working loose. And here is the good old split helical lock washer, which is a misnomer, because once you compress it under normal bolt torque, it will flatten out, and then it's just a flat washer anyway, which doesn't do anything for you. And vibration testing of the split lock washers assemblies indicate that they're about the same as a flat washer to resist vibration. And I don't recommend them for any kind of a locking situation, although I was sharply criticized for writing this in a Fastener magazine, because the person who wrote in the criticism was a manufacturer of split lock washers. So he didn't like it because I said his product was worthless for locking. Now, here is a method that is used some, but it's kind of a going a long ways to do your locking, as I see it. This is a trademark of some company on the West Coast, Stage 8, and you see what you have is a special bolt that has a it's a double-headed one with a groove machined in it, which creates a little problem on initial manufacturing. Then you have a retainer plate that slides down over this outer head onto the bottom one. Then you use this snap ring to put in that groove to lock the thing in place. Now, you do this after you've already torqued the bolt to the spot that you want it. Now, the only thing is you have to have something for this to brace against to keep the bolt from backing off. So it has to be a special design in that respect. And then the other problem that I had on the control arms on a Ford wagon, this retainer plate is made out of sheet metal. Over a period of time, it will rust up on you. And then you go to loosen this thing for a front end alignment, and the retainer plate comes off, and you can't get in there to get anything else on it to loosen it. So that one is one that I would not recommend in any environment where you would have corrosion. Now getting into washers. Now some of them we've already covered, so we won't do a lot on some of them. Most of them are flat, and they're used to provide a hardened, smooth surface for the contact of a fastener head or nut. And that's really one of the main reasons for using washers both under the head and the nut, is if you are rotating either one, usually the joint surface is not as strong as the fastener, so therefore you have to have that to avoid embedment. And then here's another one for shade tree mechanics. If you have a washer under a bolt and it's rusted in place, usually you can take a cold chisel and a hammer and knock the washer laterally and get it loosened some so that you can loosen the bolt in the washer. Now, here's the plain, flat, and countersunk type washers. This is the ordinary hardware store variety. And they're covered by all kinds of standards. There's MS, AN, ANSI, so on, which defines the outside diameter, inside diameter, and thickness for a given size. So normally you can just call out a dash number from one of these specs and you're covered. The countersunk washers are made with a countersink in them where on a high strength bolt you have a larger radius under the head. So you don't want point contact. If this diameter is tight, you could get point contact on the head radius. So you want it countersunk so that it will now distribute the load better under the head, and you won't have that high stress concentration at the radius. Now, of course, we covered the split lock washer, the tooth lock washer, and the disc lock washer. I just wanted to point out that we'd already covered those in case somebody would wonder why we hadn't. Then we go on to another unique type, and this is used a lot in the construction business, the DTI washer, direct tension indicating. It is a flat round washer that has these bumps stamped on it, but you have to use regular washers in addition to these in order to distribute the load properly, because you don't want these grinding against the head or nut of your bolt. And actually these are manufactured, and they do tests to determine the loads on them, to where the amount of compression that you get on the bumps determines the axial load in the bolt. So you torque the thing with a torque wrench without reading the torque unless you want to, down to the point that you have a certain gap left underneath the washer and the bumps, and you measure it with a feeler gauge. So this way, regardless of the coefficients of friction on the threads or the head or anything, you can actually torque it down to where the gap you get will tell you how much axial load you have in the bolt. Now here's our old familiar Belleville washers that named after the inventor who invented them way back in 1867, so they've been around a while. It's also known as a cone washer or a spring washer. And these are designed with a preload determination for a given washer for how much it takes to flatten it, and it will flatten elastically. So a lot of the times you can use them in a critical application where you want to limit the amount of axial load you have. If you put a Belleville washer on and tell the mechanic, okay, just torque this thing until the washer starts to go flat and then quit, regardless of what your torque wrench says. It also can be used for absorbing differential thermal expansion between fasteners and joint material. For instance, if you're bolting big joints of aluminum with steel bolts, so you have a different coefficient of expansion and contraction, you can put Belleville washers on to absorb some of this thermal expansion to keep from overloading or underloading the joint. You can use them in stacks, in series or parallel, in order to, in effect, use them to become a spring. Now here's another one that is kind of an oddball. You don't see them around very much because they're expensive. A self-aligning washer. You can use these on a structural shaped flange, which is usually has some taper to it. And the reason they're so expensive is the washer and nut are machined as an assembly, so you actually have a cone here, two cones that are rotating together to give you the proper alignment so that you still get axial loading on your bolt instead of putting bending on it. And this will take up to 8 degrees maximum misalignment. I don't remember now what the angle is on the I-beams and stuff like that, but I think it's less than that. I believe it's like a 3 to 5 degree or something like that. Taper on the flanges of them. Now this is another one that gives you a axial reading without using a torque wrench. And this is a PLI, preload indicating, that SPS has the patent on. And on this one, you have a regular washer, a soft inner ring, and then a ring that goes around that has capstan holes in it, and then a regular washer. And you put all this assembly on, you tighten it down, and this inner ring is actually a load cell, if you will, in that for a given amount of compression, it has been pre-calculated, the amount of load that it takes to give you that compression. So you compress it down to where this outer washer, the capstan ring, and the regular washer are grinding against each other and won't turn. That means that this thing is compressed down to where you bottomed out on this. So you check the thing, you can't turn that ring any longer, you know you've got it to a certain axial load. And they have them color-coded and available in all kinds of materials so that you can get them to use where you want to determine the load, and there's really no good way of doing it as far as measuring it. Now going to inserts, which is a very common thing around here in the aerospace world. An insert is actually, it's a special bushing that's threaded on the inside diameter and locked with threads or protrusions or a combination on the outside diameter and installed in a drilled, molded, or tapped hole. It's used to provide a strong, wear-resistant tapped hole in a softer material normally than the fastener. And you can also use them to repair stripped threads, where you've stripped the threads in a hole. Rather than going to the next bigger size in taps, you can put an insert in without opening the hole up as much. In fact, one of the places you use them is when people strip the spark plug holes in aluminum engines. A lot of the times they use a helicoil or keynsert or something. I believe they use helicoils most of the time for that. And in general, there are the two types, the one that is threaded externally and those that are locked by some method other than threads, and we'll go into them. And you can get self-tapping and all that sort of thing too. Now, the aerospace industry uses inserts and tapped holes in soft materials in order to increase the load carrying capability of pull-out. And this way you can use a smaller fastener and put in an insert. And since the insert is normally about 1/8 of an inch bigger in diameter than the internal thread in it, you can take a 1032 bolt and install it in like an equivalent 5/16 tapped hole. Here is one of the most common one, and the generic name is keynsert, although some call them a solid threaded bushing or whatever. And the insert will usually have external locking tangs. That's these tangs you see here, and when you install them, after they're threaded in, you pound those. There's a tool for pounding those down, and they extend actually past the threads here, the root diameter of the threads, to give you locking capability. The bigger diameters will have 4 of those on them, whereas the smaller ones will have 2. And of course you can get them that are not locking at all, that you use some other method of trying to lock the external thread on them. Now, they are very labor intensive to install, so you don't install them unless you have to. Here is the other type, the helicoil, which is, I believe, now owned by Black & Decker, I think, is the owner of the patent, but they're also called a wire thread. And it's usually made of stainless steel and has a diamond-shaped cross-section that will actually form internal and external threads when installed, and it's like taking a spring, if you will, and winding it down into a hole. And the diamond section part on the back goes into the existing threads, and then the diamond section on the inside is your thread diameter that you put your fastener in. Now, they're usually coated to deter corrosion and seizing, and you can get them both in locking and non-locking. You see, if you look at this, this is the non-locking here, and this is the locking. You actually have some deformed coils down in here. And this installment tang, which you may or may not be able to see on here, is broken off after installation. Now, the difference between the helicoil and the keynsert, the keynsert is only available in one length for a size. The helicoils, you can get them in different lengths. You can get them up to from 1D to 3D length, where D is the diameter of the fastener. And another thing, of course, you need to open the hole up less where you put a helicoil in. So if you're repairing stripped threads in an area where you don't have a lot of room, you can retap the hole just slightly and get it opened up enough that you can put a helicoil in it. Now, here's a kind of a more rare type. This is a locking type insert in which you have the split beam nut machined on the bottom of it. Remember, I showed you the split beam lock nut earlier. And so that you have the locking capability, But of course you have a longer insert because of this thing having to be installed, because you see this is not threaded into the hole. And these are made primarily for aerospace usage out of either A286 or Inconel 718. And since you have less external thread, you have to be careful in soft materials to make sure that you don't exceed the pullout allowable when you install a bolt in them, because of the split beam increasing the overall length. And here is one that solves some problems, but it also creates some others: the floating insert. Now, of course, if you're using, and I'll be covering this later on, if you're using countersunk or flathead fasteners, the countersink tries to self-align fastener. If you're going into a rigid tapped hole, now you have the two of them working against each other, which is not too good. Well, this solves that problem in that the insert is you have actually an insert in the bottom of this one, so that it's externally threaded just like the regular key insert. Then you have this little jobby that floats down in here, and so this will give you some self-alignment when using countersunk fasteners. But by putting all of this in it, since this has to float inside the main key insert, you have a smaller diameter internally for a given diameter externally. So therefore, you're losing some to put that floating capability in. You're losing some, so you might wind up having to go to a larger diameter insert externally than you normally would use. Now here's the self-tapping inserts. This is usually a solid bushing with either tapered external threads like a self-tapping screw like this, or you can have, and you can have them also solid with a nylock pellet here for locking them, or you can have one that they use in plastic quite a bit, what they call a speed cert. And this is used, I think, for like in electrical circuit boards and stuff like that. You drill a hole and you actually can self-tap the thing by deforming the plastic without generating any shavings. So, all right, we will continue next with unthreaded inserts, so we'll take a break for right now.